In today's session, we will discuss about the power flow diagram of a three-phase induction motor. That is the various stages in the functioning of an induction motor. That is about the input power, then the gross mechanical power, shaft power. We will try to derive some relations between these power and also a relation between torque and speed. Okay. At the end of the session, we will try to work out some problems also. Okay, so let's get started. Now, for starting with the input power. So now, as in the case of all machines, in the induction motor also, there is a stator and the rotor. And the power which is electrical power, the input electric power which is fed to the stator. Okay, so we are giving an electrical input to the stator and this is converted into mechanical power at the shaft of the motor. Okay, first we will discuss about the various types of losses that occur in the case of a three-phase induction motor. First, we will discuss about the constant losses or fixed losses. Now, these constant losses or fixed losses, it doesn't vary with the load. That is why we call it as fixed losses. Now, it consists of two types. One is a stator iron loss, okay, and this iron loss, it is also called as core loss, and it consists of two, that is hysteresis loss and eddy current loss. Okay, the next one is the friction and the windage loss. So this is due to the friction of the moving parts and also due to the effect of wind. Okay, these two losses has to be considered by calculating the power. Now here we are not considering the rotor iron loss because it is very negligible. Why it is very negligible? Because the frequency of the rotor currents under normal running conditions is very small. Okay, now as you know, this core loss or iron loss depends on the frequency. So the frequency, since the frequency is very low, we can just neglect it. Okay. Next we will discuss about the variable losses. Okay, so other than that, there are mainly two types of losses: fixed losses or constant losses and variable losses. Now what is this variable loss? There is stator copper loss and rotor copper loss. Now these variable losses depends on the load. That is, if the load is increasing, these losses will also increase. Okay. Now in order to make the things more clear, just we will go through the diagram, this particular diagram. And actually this is not a block diagram, this is like a pictorial representation of this power flow in the case of a three-phase induction motor. Now here you can see the stator and here is a rotor and this is the shaft and this shaft is connected to the load. Now the input power of the machine. So the input power is electrical power, right? So the input power which we are giving to the three-phase induction motor is this one, Pi. So Pi is the power that is given to the stator. Okay, and this power Pi minus which loss? First we have to take the stator copper loss, then we have to take the stator core loss. Okay, so we have to subtract these two losses. So this is equal to Pi minus stator copper loss minus stator core loss. Stator core loss. This will give, this is equal to PR. Actually, this PR is the input power to the rotor, which is same as the output power of the shaft. That is very important. That is, whatever power which we are getting at the output of the stator, it is given as input to the rotor. So I can write something like PR in. That means the input power to the rotor is equal to PSO. That means the output power of the stator. I can write something like this. Okay. Then from this power, then again we have to deduct the rotor copper loss. Okay. So from the input power of the rotor, that is PR, we are subtracting rotor copper loss. And this copper loss, after deducting this rotor copper loss from the rotor input, we will get the gross mechanical power, that is PM. See, This is PM. You can see here the mechanical power developed, that is PM. Okay, now again from this PM we have to deduct what? We have to deduct the windage and frictional loss. Okay, so I can write it as WIN, windage loss, and this finally will give you what? The output power. This output power is denoted by P out. It can also be written like PSH, which denotes that it is a power at the shaft. So this will give the output power. So here we can see that starting from the input side, the stator input power minus stator copper loss minus stator core loss will give the output power at the stator, and the output power of the stator is same as the input power of the rotor, and from that we are deducting the rotor copper loss. Then you will get the mechanical power PM, and from the mechanical power again we have to deduct the windage and frictional loss, and then we will get the output power. So this is actually called the power flow in the case of a three-phase induction motor. Okay, now the same thing I have explained here also, that is stator output is equal to stator input minus stator losses. Okay, and stator losses include stator iron loss and stator copper loss, and then rotor input is same as a stator input. Okay, why it is like that? Because whatever power we are giving to the stator is converted to the rotor, or it is not converted, it is transferred to the rotor through the air gap. Okay, and actually there is a conversion like whatever power, electrical power we are giving to the stator, it is converted to mechanical power at the rotor. Okay, so the entire power is transferred to the rotor through the air gap. Okay, now then we can see that mechanical power, what will be the mechanical power PM? The mechanical power PM will be equal to PR minus rotor copper loss. Okay, that is indicated in the third point. Here you can see. Okay, in the case of transformer, there is no conversion, there is only transfer. That is, whatever power we are giving to the primary winding, it is transferred to transfer through induction. Same thing happens in three-phase induction motor also. The thing is that here there is a conversion process, that is electrical power is converted into mechanical power. Okay. Now, what about the power at the shaft? The power at the shaft PSH is given by PM minus friction and windage loss. Okay, I hope it is clear up to this point. Now we will move on to the block diagram. So this is what is represented by the power stages of a three-phase induction motor. Same thing what I have explained now. That is the input power of the stator. From that we are deducting the stator copper and iron losses. Then we will get the output of the stator, which is same as the input of the rotor. From there we are again deducting the rotor copper loss, then we will get PM. That is a mechanical, gross mechanical power developed. And from that again we are deducting windage and friction losses, and finally we will get the shaft power or the output power. Okay, this is about the power flow diagram. Next we will move on to some equations which are very important. For that we will start from the equivalent circuit. We will revisit the equivalent circuit diagram of a three-phase induction motor. Now this equivalent circuit, as I told, the values which are given here represents the per phase values. Okay, so here you can see V1, it is the stator input voltage, and I1 is the current that is drawn from the supply, R1 is the stator resistance, X1 is the stator reactance, and here we have the no load current. Okay, this is a magnetizing component, and this we can take as a core loss component. Okay, now here is a current, and here we are referring everything, all the values in the rotor side is referred with respect to stator. That is why we can see that it is I2 dash, that is equal to K into I2, and E2 dash, which is equal to E2 by K. And here this, from this point, if you see the current which is entering into the rotor, we can denote it like it is I2 dash. That is just to see to the right side of that line which I have drawn in purple color. So this is a current which is flowing into the rotor. And what about the resistance, the total resistance? So because while calculating the copper losses, we have to consider only the resistance. So what is the total resistance? This plus this, right? These two we have to add. So it is actually given by R2 dash by S. So this is the total resistance which we can see to the right side. Okay, now this one actually we are splitting into two as R2 dash, that is the rotor resistance referred to stator side, plus R2 dash into 1 minus S by S. 1 minus S by S. This we take it as a load. This portion we will take it as a load, okay, and we assume that here this is where the mechanical power is developed, okay. And here, since we are taken R2 dash, if we are taken in terms of R2, it will be R2 by K squared, okay. So this is also very important. Now based on this we will derive the relations. So that is what I have written here. That is a total load I have divided into two parts, R2 dash and R2 dash into 1 minus S by S. This R2 dash you can write it also as R2 by K squared, where K is a transformation ratio. Okay. Okay, now the power input to the stator, it is given by the power input to the stator, it is a three phase, it is given, it is not three, it is root 3 V1 I1 cos phi 1. Okay, so that is the power input to the stator. Now, in the stator, there will be both the core loss as well as a copper loss. Okay, so that we have to consider. Now, we are going to derive a relation between torque and speed, because in the previous session we have drawn characteristics between, that is, slip versus torque. We got something like this. Now we will see how we can plot speed versus torque. So for that we have to get a relation connecting this torque and the speed, right? So we will just try to derive that equation. Let's start with the rotor input. Okay, so as I told before, if you see to the right side of this pink line, vertical pink line, you can see that the current which is entering into the rotor side, what is the current? That is I2 dash, and what is the total resistance? R2 dash by S. So when you multiply this, we will get the rotor power, okay, rotor input power. Okay, so that is what is written here. So the rotor input is given by 3 into I2 dash the whole squared R2 dash by S. That is, here we are writing the equation as P is equal to I squared R. That is the relation which we are using here. Power has got three relations. Either we can write it as P is equal to V into I, or V squared by R, or I squared R. Okay, so the power input of the rotor is given by 3 into I2 dash. I2 dash is the current which is flowing into the rotor circuit into resistance of the rotor circuit. That this resistance is actually referred to the stator side by S, because R2 dash by S is the total resistance. Now what about the rotor copper loss? While taking the copper loss, we have to consider only the resistance R2 dash. Okay, because this is the loss which is occurring in the rotor winding. Okay, that is why we are taking it as R2 dash, because I already told you that is R2 dash by S. We can split this R2 dash by S into two, that is R2 dash and R2 dash 1 minus S by S. So while calculating the copper loss, we will take R2 dash. While calculating the power, we will take R2 dash by S. Okay, now from this we can develop an expression for the mechanical power. So the mechanical power developed at the rotor, that will be rotor input minus rotor copper loss. So we already derived the expression. So it is 3 I2 dash the whole squared into R2 dash by S minus copper loss. So we can simplify it like this. So this is actually the first expression for PM. So we got PM is equal to, this is PM, PM is equal to 3 I2 dash the whole squared into R2 dash into 1 by S minus 1. Okay, now our intention is to get a relation between torque and speed. So still we are not finding any speed term here, right? So we will see how to bring that term. For that, now we will derive another equation for this PM, and then we will equate it. Okay, so we already know that the power, torque and speed are related by the equation P is equal to T into omega. Okay, the same relation we will apply here also. So here I am applying that equation, that is PM. I can write, I can write, just 1 second. Okay, so now I can write PM is equal to T into omega R. Okay, so what is this T? T is a torque. Okay, and what is omega? Omega is the angular speed. And here you can see NR is the rotor speed. Okay, now I'm equating this, I'm taking this as equation number 2. So if you see the first equation and second equation, the left hand side both are PM, right? So I will equate it, then I will get what? 3 into this equation, 3 into I2 dash the whole squared R2 dash 1 by S minus 1 is equal to, this is the one. See this expression is equal to, I am equating it, equation number 2. That is 2 pi nr by 60 into tg. Here you can see already we got a speed term here. This is what we want because we are going to find a relation between torque and speed. Okay. Now next we will see what are the substitutions we can do here. So here you can see one term I2 dash. Okay, so instead of I2 dash, I will put it as K into I2 and I will substitute for the expression I2 which is given by E by Z. Okay, this is rotor, so it is SE2 by square root of R2 squared plus SX2 the whole squared. Similarly, I will substitute for R2 dash, that is R2 by K squared. Okay. Now I am again equating this expression because here I substituted for all those I2 dash and R2 dash. And again one more substitution I will make. Instead of the rotor speed nr, we know that nr is equal to 1 minus s into ns. So that relation I will put it here. So I'm substituting so many equations here. Okay. So instead of nr, I will put it as 1 minus s into ns. Again, I'm equating these two equations, and finally what I'm getting an expression for the torque. See, the torque I will get it as 3 by 2 pi ns into s into E2 squared R2 by R2 squared plus SX2 the whole square. Now this equation is very important, and here you can see which all here you can see that the torque and the speed are connected here, and also we can see one term slip here, and there is rotor resistance, rotor reactance, and the supply, that is induced EMF proportional to supply voltage also. So this relation is very important because you will be using this equation for doing problems. Okay. Now next, moving further, there are some other important relations also which we can derive. Now the rotor output, it is given by, I am using the equation P is equal to T into omega. Based on this relation, I can write it as the torque generated into omega r, right? So omega r, instead of omega r, I can write 2 pi nr by 60. This is the rotor output. What about the input? That is also T into omega, but here you have to take the synchronous speed because it is a rotor input. Rotor input is same as stator output. Okay, so that is why I'm taking the speed ns instead of nr. Now let's find the rotor copper loss. So what will be the copper loss? It will be output minus input. So I have to subtract rotor output and rotor input. So these two equations, that is, suppose if this is equation number 1 and suppose if this is equation number 2, then I will subtract which minus which? 2 minus 1. Then I will get this relation. Okay. Now I am taking the ratio of rotor copper loss to rotor input. So rotor input equation I already know, and the rotor copper loss also I calculated. This is the equation for the rotor copper loss, this one. Okay, so let me take this equation as 3. Then I am going to find the ratio of rotor copper loss to rotor input. So actually it is 3 third equation divided by second equation, 3 by 2. Then I will get this expression, that is rotor copper loss by rotor input is equal to slip. Okay, this is a very important relation. That is, suppose if you are asked to find the rotor copper loss and if the rotor input is given, you can use this relation. Rotor copper loss is equal to S into rotor input. In the same way, we can find a relation like rotor output is equal to 1 minus S into rotor input. Because rotor output is what? Rotor input minus rotor copper loss. That means rotor input minus, instead of this rotor copper loss, I will substitute this equation. Okay, so you will get this expression. So these two equations are also very important. So how many equations we learn now? That is the equation connecting torque, speed, slip. That is this first equation, Tg is equal to 3 by 2 pi ns into S into E2 squared R2 by R2 squared plus Sx2 the whole square. Okay. Then we learned the equation rotor copper loss is equal to S into rotor input and rotor output is equal to 1 minus S into rotor input. These equations are very important. Okay. Now let's based on this particular equation, let's see the speed torque or torque speed characteristics of a 3-phase induction motor. So already we discussed about the torque slip characteristics, but here it is torque speed characteristics. So just to see here, now along the x-axis I have taken the speed. Okay, and this speed, if you see, it is increasing from the left to right. Okay, now let's start from this particular point. We'll take this point. Now if you see here, let's just assume that the speed which I'm taking is the rotor speed. So at this point, when the starting condition, you can see that the speed of the rotor NR is 0, right? NR is 0 and the value of slip is 1. Value of slip is 1. Okay. So that, and what is a torque? You can see here that there is a starting torque. How do you get this? Because in the torque equation, you substitute S is equal to 1, then you will get the value of the starting torque. But the speed of the rotor is 0 here. Okay. Then slowly what happens? The rotor starts rotating. That means the value of NR is going to increase. Slowly the rotor speed will increase. Okay, when the rotor speed is increasing, what happens? Slip value will reduce, right? And you can see that it will reach this particular point where maximum torque is developed. And you know, when a further increase in the slip, the torque will not increase, but torque will reduce according to the relation T inversely proportional to slip. Now let us consider this particular point. At this point, you can see that the rotor speed becomes almost equal to the synchronous speed. That means slip is 0. See? So at this point, slip is 0 and the rotor speed is equal to synchronous speed. Whereas here it is slip is 1 and rotor speed is equal to 0. So when you are drawing these characteristics, actually you can draw the torque slip characteristics and torque speed characteristics together. Here I have expressed speed along the x-axis, and that is just to see the direction of the speed. It is from left to right. Now what I can do is, if I want to indicate the slip, torque slip characteristics, just I have to put slip like this. It will be from right to left. So I can put this as slip, because see the value of the slip on the right hand side, the value of slip is 1. Sorry, slip is 0 and it is slowly increasing, and at this left hand side it is becoming 1. So just to see the direction in which I have indicated the quantity slip. Okay, so the conclusion is torque slip and torque speed characteristics can be indicated together in a graph. Now next we will discuss about the 3 different modes of operation of a 3-phase induction motor. Now here so far we have discussed only the motoring operation of a 3-phase induction motor. This is what this portion we have already discussed. That is like there will be a starting torque, there will be a maximum torque, and then the torque will become 0. Okay, and what about the slip? The value of the slip is varying between 0 and 1. So this is the motoring region. Now other than this, there is another thing called braking region and generating region also. So in the generating region, what happens is, you can see here slip is less than 0. So how we can make the slip less than 0? So slip is given by the equation ns minus nr by ns. So if slip has to be less than 0 means what is the condition? The rotor speed should be greater than, that is, suppose if ns is 1, if I am taking nr as 2, then the value of s will become negative, right? So that means for this condition, the rotor has to be run at a speed more than the synchronous speed. Okay, so that time actually it is acting as a generator. So it will be providing the electrical output. Okay, so that is called the generating action, and in this mode the slip will be less than 0. Okay, now what about the braking region here? In the braking region, we will just try to analyze the same equation, that is S is equal to, slip is equal to ns minus nr by ns. So the condition is that slip should be greater than 1. So how can you get that slip value greater than 1? That means this sign has to change. It has to become minus nr. So the slip will be like ns plus nr by ns, which means, what is the meaning of that? The rotor speed has to reverse, or you have to run the rotor in the reverse direction. Okay, so that is how you can operate it under braking mode. Why we need this braking mode? When we want to stop the motor, when we want to reduce the speed, and when we want to stop the motor, we have to go for this particular mode. Okay, so that is indicated here. That is, we have 3 regions: low slip region, that is when the slip is less than 0, then medium slip region when it is in the motoring mode, and high slip region when it is in the braking mode. Okay, so this I have already explained, the motoring mode where the slip is varying from 0 to 1. Okay, a moderate variation. no load condition, that it is 0, and 1 at standstill, the value of slip. Now I have discussed about the generating mode also. That is, here what we are doing is both torque and slip both will be negative, and we are actually running the motor, that is the motor runs above the synchronous speed. And what about the braking mode? In the case of the braking mode, here we have to stop the motor, so we have to start it rotating in the reverse direction. Okay, and slip will be more than 1. Okay, this is what we have discussed using this particular relation or a particular diagram. Okay, so S will be greater than 1. Now based on this, now we will try to work out two problems. Okay, so it will be more clear. Now just go through this question. A 6-pole 50 Hz 3-phase induction motor runs at 960 rpm when the torque on the shaft is 200 Newton meter. If the stator losses are 1500 watts and friction and windage losses are 500 watt, we have to find the rotor copper loss and efficiency of the motor. Now here the frequency is given, the number of poles is given. Okay, using that we can calculate the synchronous speed, 120 F by P. Okay, now here it is given that the motor runs at 960 rpm, which means the rotor speed NR is 960. Using that we can find the value of slip, that is ns minus nr by ns, and then we will get the value of slip. Next it is given that the shaft torque is 200 Newton meter. Okay, so if the shaft torque is given, then we can use the relation like a P shaft or P output is equal to torque at the shaft or output torque into the angular speed of the rotor. This relation we can use. Okay, and this omega r is equal to 2 pi into nr by 60, where the speed of the rotor is in rpm. That is why we are putting 60 here. Okay, so applying that equation here, we can calculate the power. Okay, so the rotor output power or power at the shaft is given by 2 pi nr into tsh by 60, and we will get this. Okay, so now we got the rotor output power which is at the shaft. Okay, and we know the relation that whatever power which is developed by the rotor Pm, it minus windage and friction losses is equal to the P shaft or the P output power. So which means in order to generate or in order to get the value of this gross mechanical power, add this losses to this one PSH. Okay, so that is what is done here. Pm is equal to PSH plus windage and friction losses. Then you will get the value of Pm. Okay, now next we have to find the rotor copper loss. So we have already learned this relation. Rotor copper loss by gross rotor output is equal to S by 1 minus S. So using this relation we can find the value of the rotor copper loss. So rotor copper loss is given by this S by 1 minus S into gross rotor output. Gross rotor output is Pm. It is not PSH, it is Pm. And then you will get the value of rotor copper loss. So once you get the value of the rotor copper loss, we can find the rotor input. Okay, because rotor input is same as stator output, and that is equal to rotor copper loss plus rotor output. So rotor output already we got it here. See here, 20596. So to 20596 we have to add the rotor copper loss. Then you will get the rotor input. Okay. Now rotor input and stator output are the same, that is given here. So we got the stator output, and to the stator output if we add which loss? Stator core loss, then what we will get? We will get the stator input. Okay, so if we consider this induction motor as a machine, this is the stator and this is the rotor. So here it is the stator input power which is Pi, and here we have the shaft output power Po or PSH. So PSH by Pi into 100 will give the efficiency. So Pi, now we calculated Pi, that is a stator input. Okay, so that will come in the denominator, and the numerator you have to take the power at the shaft, not Pm. Here we have to take PSH or P output. Okay, so PSH or P output we have calculated there. Okay, so that value we have to substitute. This is the P output or PSH. So that value will come in the numerator. Okay, so actually we have used so many equations here. that is ns is equal to 120 f by p, s is equal to ns minus nr by ns. Then we have used the relation here, p is equal to t omega, right? Then we have used the equation rotor copper loss is equal to 1 minus s into gross rotor output. So many equations we have used. Okay, so we have to be very thorough with the power flow diagram and these equations, then only you will be able to do these problems. And we will try to work out one more problem. The power input to the rotor of a 440 volt 50 hertz 6 pole 3 phase induction motor is 100 watt. That means power input of the rotor is given. Voltage is given, frequency is given, number of poles is given. Okay, then based on that, we can calculate the synchronous speed. There is no problem that because it is 120 f by p. Frequency is 50, p is 6. Then here there is one very important statement, that is the rotor electromotive force is observed to make 120 cycles per minute. The rotor electromotive force, that means EMF generated in the rotor, that frequency f dash we can find. That is 120 cycles per minute. That is why we are taking it as 120 by 60 and you will get it as 2 hertz. So this is a slip frequency. That slip frequency is given by slip into supply frequency. So from that we can find the value of slip. F is given, f dash is also we have found. Then we can find the rotor speed based on the relation nr is equal to ns into 1 minus s. That also we got. Then already we know that the relation between rotor input and PM, mechanical power developed. That is PM is equal to 1 minus s into rotor input. So very easily we can find the rotor input. And also we have learned this relation, how to find the rotor copper loss provided the rotor input is given. It is total rotor copper loss is equal to S into rotor input. That also we can find. So it is very easy. Now we have to find the copper loss per phase because in the question they have given find the rotor copper loss per phase. So just you divide it by 3 and you will get per phase value. Okay, now next last step is to find the line rotor resistance per phase if the rotor current is 60. So current is given and already we know this relation, that is what is the relation for power. We are using the relation power is equal to I2 squared I2 dash squared into R2. From this we can find the value of R2 because power is already given, that is we have calculated the power here. Yeah, okay, that into 10 raised to 3 because we have to convert it into watts because current is in amperes. Okay, and then we will get the value of rotor resistance. Okay, so I hope you got an idea about this today's topic. So just you have to understand clearly about that power stages in a 3-phase induction motor and also the various equations.